06. What date is it today? Anyone know what's so special about the 7th? No, I don't know. I didn't even know what it was until just a few days ago. I still don't know what it is. Uh, Speaking of 6-7, um, Domino's has a code where if you enter 67 promo code, you get a large one topping for $6.70. So I don't know if it has anything to do with it, but it works. I mean, I tested it out. It works on their website, and it works in California. More importantly, without adding a dollar on it. So $6.70 buys you a whole large pizza. Okay, chapter 4, comment based. There we go. Now the special thing about today is that it's Marie Curie's birthday. Okay, Marie Curie was the first woman to win the Nobel Prize. Everybody knows that. But she's one of only 4 people to win 2. And she's the only woman till date to win 2. Okay, she won the first one in conjunction with her husband and a physicist for physics. And then she won a second one, more importantly, in a different field. She won a second one in chemistry. So she's the only one who has won it in 2 different scientific fields. Only person. The other 3 people who won, second one was Paul Linus, or Linus Pauling, I believe. He won it for physics, and then he won in second category, Nobel Peace Prize, for protesting and working against nuclear testing. And then let's see, Sanger, Frederick Sanger, I believe, won 2 in chemistry. He is known as the father of the human genomics field. So he did a lot of research in that field. So DNA sequencing, genome sequencing, that all goes back to his work. He won it decades apart. He won the first one in 1958, the second one in 1980. So more than 2 decades. That's amazing. And then let's see, what else? Oh yeah, here's what you should actually know. The 4th person to win twice was John Bardeen. You saw him in E306 in one of the slides. John Bardeen, William Shockley, and Walter Brattain are credited with the invention of the transistor, the solid-state transistor. So John Bardeen, well, all 3 of them had a falling out later because of one person, I think Brattain or Shockley, I can't remember which one. And then they all went their separate ways. Bardeen went on to join, I want to say UIUC, or maybe it was Chicago. Can't remember which one. So one of the Midwest universities. And he did research in superconductivity. So he won a second prize in physics based on his work. So there are only 4 people who have won more than one prize. A bit more about the Curie family. So Maria was from Poland. She came to France to do research work because it was not permitted for women at that time. I guess that's where she met Pierre Curie, met and married him, and they did work together in the field of radiation. And they won the prize in physics. A few years later, she won the prize in chemistry. And she shared it with 2 other people. She shared it with her daughter and her son-in-law. So her daughter and son-in-law are also Nobel laureates. They had a second daughter, so the younger daughter, and the younger daughter married, can't remember his name, but anyway, the younger son-in-law also won a Nobel Prize. He won it in the category Nobel Peace Prize. So 5 members of the same family. Talk about overachieving and underachieving. Anyway, I find all of that history very fascinating. So November 7th. And let's see, and any of you go on to do that, please come back and see me. It's $1 million prize. Okay, all right, chapter 4. Where are we? Common emitter, common base, and common collector. Why is this not behaving? Okay. Oh, there we go. Finally. So we covered this. Yeah, biasing modes. Biasing modes. What is bias? Anybody remember? Electrically speaking, what is bias? You remember very well. I like to think, I'll take credit. You perhaps know this from other classes, of course, too. But bias is, as pointed out, bias is the state of preparing a circuit to accept input. So when we say bias or we refer to bias or biasing modes, we are talking about applying DC voltages and DC currents to our circuit or to our devices in so that they're prepared to receive AC input. When it comes to diode, we apply a bias to turn our diodes on or off. When it comes to transistors, we apply a biasing for them to either operate in the active region or in the cutoff or the saturation region, right? And so from the biasing, we arrived at, or we talked about Q points. The Q stands for quiescent. Quiescent basically means dormant or lying in wait. So as far as our electronics is concerned, we apply a DC bias to our circuits, and then we set up the Q point or the quiescent point. Having a lot of trouble with that word, quiescent point, also known as the operating point, so that our circuit functions exactly as we want it to, right? That's also what we do for Lab 8. We need to design a circuit to operate as an amplifier. Anyway, so based on that, what we have is 3 modes of operation: common emitter, common collector, and common base. Each one of these modes has their pros and cons, but the most common by far is the common emitter. Okay, common emitter or CE mode. Okay, common base and common collector are not that common. Have to make dad jokes, a few of them. Okay, so depending on our biasing circuits and depending on the mode of configuration, meaning which terminal is common to the input and the output side, we have common emitter, common base, or common collector. Okay. All right. The CE mode has a few advantages. It has high input impedance, it has low output impedance, and we can use a single supply to bias both the input and the output. If you perform the lab 7 specifically, if you recall, we have a separate instrument on the input side and a separate instrument on the output side, right? So we need 2 biasing supplies. Common emitter amplifier with voltage divider bias, we can use one single supply to actually bias both the input and the output. Okay, that's what makes it a little bit special. So based on these biasing modes, we have input characteristics and output characteristics. Here we are looking at NPN and PNP configurations for biasing. Everything remains the same. Since the electrons and holes are swapped together, the flow of currents and the voltages is exactly the opposite. Other than that, there is absolutely no difference. Okay. So on the output side, we plot our characteristics. We plot IC as a function of VCE. Okay. IC as a function of VCE. This is the x-axis right there. Collector current as a function of the collector voltage, VCE. All right. What do we see? We see that similar to FETs, there is a sort of linear behavior when VC first increases, right? That's the applied voltage. And then it takes a sharp turn towards the right, and it quickly reaches a saturated level and behaves almost like a constant current source. Okay. So these lines are, they're pretty flat, but these are ideal characteristics. This is not true of real performances. Okay. So for every value of the input current, we can have a sweep of data points of IC as a function of VCE. We can divide these into three major regions. That's something that we'll look at in the next slide. This region right here at the bottom is the cutoff region. This is the forward active or just the active region. And this is the reverse active where we do not see anything. Okay, it's simply collector current basically just does not exist. If you'll recall from the sweep and go simulation of a reverse bias PN junction diode, nanoamps or less, right? That's what it would be. And then this here sometimes gets confusing because the triode region in the FET is known as the saturation region in a BJT. So here to the left of the active region, that's the saturation. Okay, so all of this is the saturation region. All right. Okay. All right, let's take a closer look. So again, IC as a function of VCE. IC is in milliamps, VCE is volts. Again, saturation region is here in the shaded area to the left. Active region is all of this. And then cutoff is like right there, where it's cut off and then there's no current flowing through. Okay. Here shows a bit more realistic where the slope actually increases. Right? So you can see that the slope actually increases. And of course, depending on the behavior of the circuit, depending on the model of the transistor, there are variations in performances. Okay. But when we set our Q point, what we are doing is, let's say this is our load line, for instance, right? This is our load line. We want to set our operating point somewhere in the middle. Okay. Especially if you want it to work as an amplifier. If you want to amplify signals like base current, amplified output current on the collector side, then we want to bias it to operate somewhere in the middle of the active region. If it shifts up or if it shifts down, then we have clipping, which would be audible as distortion on the audio speakers. Okay. All right. What other things do we notice? We see that VCE is very, very small. So VCE sat or VCE saturation is very, very small. So typically, if VCE is less than or equal to 0.2 volts, it's in saturation. So it's on the left side of the graph. If VCE is more than 0.2 volts, then it's typically in the active region. Okay. Let's look at the input side or transfer characteristics. All right, collector current IC is a function of input VBE. It's common emitter mode, biased, C, sorry, not C. Base emitter junction forward bias, collector base junction reverse bias. So if the base emitter junction is forward bias, it's a forward bias diode, meaning the characteristic looks like a diode forward characteristic. So it's similar to a PN junction diode. Okay, PN junction diode. And because we are talking about output current and the input voltage, this chart shows us how the input is being transferred to the output, hence transfer characteristics. The straight line is simply showing you the slope. I'm sorry, it's plotted in log scale on the right, and that's what it's showing us. And so when you plot it on the log scale, we have a straight line with a slope of about 60 millivolts, I would say minus 60 millivolts, plus 60 millivolts per decade. That's the approximate slope. Okay. So those are the transfer characteristics. Right. So we'll go through the fundamentals, and then for at least a week or so, we want to just look at different circuits and learn how to analyze these kind of circuits, right? Okay, let's look at circuit models. So here's the circuit model for the forward active region, right? Forward active region. On the input side, we have a forward bias junction. So we can model that as a PN junction diode. And it drops a voltage of VBE across its terminals. On the output side, we have the collector current. The collector current behaves like a dependent current source that depends on IB. And so you have IC equal to beta IB. And because IC is IS e raised to VBE, that dependency is on input voltage VBE. So we can describe this as a voltage controlled current source. Okay, voltage controlled current source. That's what you can describe it as. It's because output collector current IC is beta times IB. Okay. And you can further simplify this by using a constant voltage drop model, CVD model. The CVD model, the diode is replaced with a constant voltage source of 0.7 volts. Okay. Again, this is just an approximation. This is a model, right? It does not, this model is not valid for all environments because VBE is not going to be fixed at 0.7. It would change depending on the circuit conditions and parameters. Somebody on Zoom, please send a message. All right. Let's take a pause. Let me know if you have any questions. Yes. Uh-huh. Uh-huh. Yes. Good point. So here we are actually not using, but we can say it's a current controlled current source. If we analyze from the perspective of VBE, the input voltage, you can say it's a voltage controlled current source. If you analyze it from the perspective of IB, then it's a current controlled current source. Whichever model fits our analysis, we are free to use. So we have two equations for IC, right? Beta times IB or E raised to VBE. Okay. Any other questions? Okay. Let's look at an example of the forward active model. In this, we are okay. All right. NPN transistor, biasing is simple, no other resistors, as straightforward as it gets. Okay. VCC is provided on the output side, constant current IB on the input side. No variations. IS is 10 raised to 16 or 10 raised to minus 16 amps. Alpha can be determined or is given as 0.95. And you're asked to find the terminal currents, IC, IE, and VBE, and VBC. Okay. If any of these quantities are not given, you can assume, right? If saturation current is not given, assume some value like 10 raised to minus 15, 10 raised to minus 14, 10 raised to minus 16, any value you want. What else do you think you would need? Thermal voltage, VT. We always need that. So again, if it's not provided, just assume a value. Typically, it's 25.8 at room temperature of 27 degrees C. You can take 25.8 or 26 or 25 millivolts. Let's just keep it straightforward and assume VT of 25 millivolts. Okay. 25 millivolts. Then let's assume that this is operating in the active region, right? There's only three options. It's either active or cutoff or saturation. If you assume cutoff, well, then output current should be completely equal to zero or as close to zero as possible. If you assume saturation, then we perform our analysis. If VCE is 0.2 volts or less, then it's in saturation. Or we assume active mode, and then we determine VCE, VBE from those values. Okay. So we assume VT and we assume active mode of operation. That means, what does it mean for VBE? It's 0.7 volts. So if you assume active mode, we have one less quantity to find. It's not that we don't have to find it. We do have to find it, but it's a starting point for us. It's one less unknown to worry about at the beginning. What else? What else do we have? How about terminal voltages? We have VB, VE, and VC. What is VE? What is VB? What is VC? Absolutely. So we already have our terminal voltages. So at the beginning of our analysis, we should always extract as much information as we can from the given problem statement, from the images, circuit diagrams, graphs, charts, everything. Okay. All right. So we have VE0, VB is 0.7, VC is equal to VC is equal to 5 volts. So now what is VBC? So it will be VB minus VC. 0.7 minus 5 minus 4.3 volts. Oh. What else do we have to go on? We have IB. IB is 100 microamps. Can we calculate IE from there? We can, but the easiest thing to calculate from IB is it's right there, IC. So IC is beta times IB, but we are not given the value of beta, right? But we can calculate beta from alpha. Alpha over 1 minus alpha times IB. All right, calculators out. Perform this calculation. Tell me what answer do you obtain. Times, what is this, 100 microamps? What do you obtain? Anyone? That is correct. 1.9 milliamps. But follow the logical thought process of how we arrived here, okay? So now that we have IC and IB, we also have beta. We can use either one of those relationships to calculate IE. IE is the total current split between the base and the collector. IE is IC plus IB. So we add them together, we obtain IE, or it's beta plus 1 times IB. Either ways. So IE is what? Sorry, IE is IC plus IB. IB is 0.1 milliamps. Sorry, 0.01 milliamps, or 110 is to minus 6.1. Okay, so IE is 2. And then once we have that, we can find VBE by applying it to the equation that we have for VBE, which is VT ln IC over IS. That's from the forward active models. VBE is equal to VT log of IC over IS. 0.025, 25 millivolts, log of 1.9 into 10 is to minus 3, and IS is 10 is to minus 16. All right, calculate and let me know what you obtain. Doing this is good practice for the exam when everyone would have to do this. Whether it's on your own calculator or whether you're using an app, doesn't really matter. What did you obtain? 0.764. Yep. So not quite 0.7 volts, 0.764. That's how it changes. So a little bit of iteration now. Okay, let's take a pause while you go through the steps, see if they make sense. Right? It's a model. A model is typically an approximation. All models, I mean, a single model does not suffice for all scenarios. In this case, we have a simple circuit, no biasing resistors. You're simply applying a voltage on the output side. You're applying an input current on the base side. And then we're trying to find the terminal voltages and the currents. So anytime you're faced with such a problem, these are the steps that you should take. Extract all the information as you can, list it all down with all the quantities along with its units. Make an assumption about the mode of operation. In this case, I'm assuming an active mode of operation. If it's active mode, then logically VBE should be equal to 0.7. From there, I'm looking at the circuit, and inspection and observation gives me V equal to 0, VB is 0.7, and VC is 5 volts. Determine VBC from there. From VBC, try to find IC. From IC, I found IE. From IE, trying to find, not IE, sorry, from VC. From IC, trying to find VBE. And once I found VBE, I see it does not match up with my assumption. Assumption is about 0.7. My answer is about 0.764. Without going through further analysis or multiple iterative steps, I'm going to halt this. But before I halt, I want to find my actual VBC based on these values, right? I'm going to take this and I'll plug it in here. And I will find my new value for VBC. Okay, VBC, VB minus VC, to be 0.764 minus 5, and that gives me minus 4.24 volts. So not too far off, but when we talk about millivolts and milliamps and microamps, that it makes a big difference. Okay. All right. Let's take a pause. Let me know if you have any questions. Any other questions? Any questions? Sorry, not other. No questions? All right, let's see. Yeah, we have enough time for do another problem. Okay. Okay, let's go to the next example. How many of you are traveling for on Monday? Is everybody in town? If you're traveling, too bad, you're gonna miss the quiz. So there is a quiz on Monday. Not kidding. I'm serious. There is. I'll be here. I ain't going anywhere. I ain't going nowhere. All right, forward active mode, example 2. Now we have two biasing resistors. Base is connected directly to ground. But look at the voltages. Let's take 10 seconds, extract all the information as you can. How many power supplies are connected? Plus 9 volts and minus 9 volt. If I was to draw this out, I could draw it out like this. This sometimes not sometimes, it often helps me visualize things and apply KVL much better. That's it. That's the circuit. So this is 9 volts. This is also 9 volts. And this is 8.2K and 4.3K. All right, that's the circuit. All right, and then we have our terminal voltages. We have our terminal currents, IE, IC, IB, VBE, VC, VB, VC, and VE. Okay. So we can draw it out as shown on the left, or we can draw it out as shown on the right. We have, we want to determine the Q points, meaning the value for the collector current and the collector emitter voltage, IC and VCE. So determine the Q point, meaning IC and VCE. Okay. What circuit analysis techniques come to mind? Seriously? Should be almost automatic at this point. There's only three circuits to choose. I mean, three techniques to choose from. There's Ohm's law, there's KVL, there's KCL. That's it. If we are talking about currents, we apply KCL. If you're talking about voltage, we apply KVL. Those are the only two. There's nothing else. All of circuit analysis is just based on these three. Right? So we can apply KCL, yes. But if we apply KCL, we don't have any of the current values. Right? KCL we can apply, but we already know that IE equals IC plus IB. That's the only equation we can think of. So if KCL is not an option, that only leaves us KVL. So we apply KVL. We could apply Ohm's law, but again, we don't have any other, any other terminal voltages, or we don't have any other currents. So again, Ohm's law is also out. The only thing that is left is KVL. So KVL, we applied in this loop, we applied in this loop, in this open model, can be applied like this, or applied like this. As engineers, you should be able to think and apply to both renders of these diagrams. Okay. All right, so let's call this the input side, not call this. This is the input side, and this is the output side. So let's apply KVL on the input side first and generate some equations. These look very small on the projectors, by the way, but it's very large on the screen here. All right, so what do we have on the input side? How many voltages do we see? By the way, this is not the input, okay? That's the output side, the collector output side. It's just biasing supplies we are showing on that side, that's all. Doesn't mean anything else. So input loop, how many voltages do we see? Let's call this VCC. Let's call this VEE. So what do we have? We have minus VEE. I'm starting from the bottom left corner of that loop, going minus VEE plus VBE and plus VRE equal to 0. 3 voltages summing up to 0. All right. Now, VRE is the voltage drop across the emitter resistor RE. Let's, 7 minutes left. Let's pick up the pace. And let's assume active mode of operation. So we have one less unknown to worry about. Therefore, VBE is equal to 0.7 volts, right? So minus 9 plus IERE or plus 0.7, and this would be IE times, what do we have? 8.2K, so 80 to 100 equals 0. You can calculate IE from here. We can write IE is 8.3 over 80 to 100, and therefore IE is 1.01 milliamps. And that's it. That's more than half the work done, so to speak. If you have IE, then we can calculate IB and IC from there. Oh, one thing I missed. Beta is given. So beta F, the forward is given as 50. Reverse, typically inconsequential, is given as 1. Okay. So far, so good. Apply KVL. The only unknown is IE. So we solve for IE, obtain an expression. IE is the sum of IC plus IB. IC is beta times IB. And so I can write IE as equal to beta plus 1 times IB. So IB outside, beta plus 1 IB. Beta is 50. Plug it into the equation. And so I can write IB is equal to 1.01 10 raised to minus 3 divided by 50 plus 1. In this, you can perform the calculation. I'm going to write the answer. Comes out to be 19.8 micrograms. All right, let's take a short pause while you catch up and let me know if you have any questions. From the value of IB, tell me what's IC. Well, calculate and let me know the value. Sorry, what? Sounds about right. All right, so we have our three terminal currents, IE, IB, and IC. Any thoughts on how we can go about finding VCE? Right, it's the output side. We need to verify. Need to verify this. VCE. Well, we shouldn't need to have a thought actually. We just did KVL on the input side. So sorry, what? It is IC times RC. That is one of, yes, that is one of the terms in the equation. But how do we generate an equation? By applying KVL on the output side. And yes, we would obtain VCC minus ICRC. Very commonly known as the ICRC resistor collector, collector resistor drop, ICRC drop. So apply KVL on the output side and generate our second equation. And then what do we obtain? We got VCE equals VCC minus ICRC plus VBE. Okay. And that's here. Actually, we went here also. Okay, makes it one less term. And so VCE is equal to 9 minus 0.99 milliamps. RC is 4.3 K plus 0.7. The bell has rung. If you have to leave, you can leave. I'm going to just finish this problem and you can watch the recording later. Therefore, my VCE, once I calculate this, is 5.44 volts. And because my VCE is greater than 0.2 volts, it is not in saturation, it is in active mode. And hence my assumption is verified. So my final act would be to write my final answer. Therefore, Q point is the coordinates of the Q point is 0.99 and 5.4. This would be a professional engineer's layout or presented outside. 0.99 milliamps, that's ICQ, and 5.44 is VCEQ. Okay, the Q simply stands for the value of VC and IC at the Q point. Okay. All right. We'll end class here today. If anyone has questions, I'm happy to answer those. But if you're gonna leave, I'll wish you a good weekend and I'll see you all on Monday. Homework assignments, reading assignments have been posted. All of them are available on Canvas and on Connect directly. Keep up with the reading. The reading is all extra credit. So the more you read and understand and answer the questions, more you can earn your points. And then homework assignments, one is due on Monday, the next one's due a few days after that. All right, I'll see you on Monday.